Hello everyone, and welcome back to a new episode of Advent of Code. We are almost caught up. In fact, I feel like I should be able to do part 7 before 2 hours and 40 minutes have elapsed, so I will be caught up to live, and can maybe start doing a live stream or two. We'll see. I don't know. Live streams are a bit more work, but it would be nice to do a couple of them anyway. Alright, let's dive into part 7, I guess. Day 7. Recursive Circus. Wandering further through the circuits of the computer, you come upon a tower of programs that have gotten themselves into a bit of trouble. A recursive algorithm has gotten out of hand, and now they're balanced precariously in a large tower. One program at the bottom supports the entire tower. It's holding a large disk, and on the disk are balanced several more sub-towers. At the bottom of these sub-towers, standing on the bottom disk, are other programs, each holding their own disk, and so on. At the very tops of these sub-towers, many programs stand, simply keeping the disk below them balanced, but with no disk of their own. You offer to help, but first you need to understand the structure of these towers. You ask each program to yell out their name, their weight, and, if they're holding a disk, the names of the programs immediately above them balancing on that disk. You write this information down. That's our puzzle input. Unfortunately, in their panic, they don't do this in an orderly fashion. By the time you're done, you're not sure which program gave which information. For example, if your list is the following, and so this is what our input's going to look like: a program name, a weight, and possibly a set of subprograms, the programs above them. And so this all forms a nice orderly tree. We're guaranteed there's no like loops or anything. There's a bottom program supporting everything, some number of programs in each tower, and so on. And so, well, the question we're asked is, what is the name of the bottom program, i.e. the one at the root of the tree? So, how to solve it? I confess that I read this problem solution last night, I guess, and I put a little bit of thought into what the approach will be and what problems we might run into. So the first obvious thing that we're going to want to do is like convert each of these lines into a meaningful Haskell data structure. We'll have some type that represents the information in one of these lines, basically like a program's name, its weight, and a possibly empty list of children. Simple enough. So that'll be like step 1. And then, from there, there's a few things that we could do. One, which would be the simplest way, I think, easiest perhaps, would be, look, all we're really looking for is the one program which is not in any other program's list of children, right? We could just go through all of the programs and compile a list of all of the children we've ever seen, and then go through the list of programs again, looking for a program which is not in that list. We could do that. And that would get us the answer to part 1. But there's going to be a part 2, and I doubt it'll be that. It'll be something we can solve in that way. We'll need to understand the tree structure of the programs for part 2, and we'll need to know something about the weights, like surely these matter, right? So what I would like to do is just reconstruct the tree structure exactly as is, so that we have sort of a perfect understanding of the problem conditions. Build a tree. And I did a little thinking about how that's going to work. Because it seems actually quite difficult to build a tree in sort of a random access fashion, right? Where you're just given a node that exists, and you're like, all right, better put that node somewhere, and then you get another node that eventually connects to it, right? It's like kind of hard. You could do it in a sort of imperative language by keeping like a hash map from name of program to subtree underneath that program, and gradually sort of put things together, maybe like leave blanks for when you get to a program Like, if you read FWFT's node, but you haven't yet constructed KTLJ's node, do you leave that spot blank? Do you, like, I don't know, it's still a little bit hard. And it's even harder in Haskell where you can't update this tree as you're building it. So that approach kind of seems like a non-starter. But I thought about it a little bit more, and I realized it's actually easier when you don't try to modify anything. In Haskell, when you're building a data structure, you kind of like to build it from the bottom up rather than the top down. That is to say, it's very difficult to start with the root of the tree and gradually add things, because you can't modify the root. But if you start with the leaves, you can easily build nodes above those pointing to the existing leaves, no problem. But that's hard to do because we don't know the ordering, right? And so what you can do instead is you can actually, I think, we'll see, but I think you can build the whole tree all at once and not even ever understand what the dependencies are, which seems incredible. How could you do such a thing? We're going to use a technique called tying the knot, which is sort of a Haskell... I mean, you could do it in languages other than Haskell if they supported lazy evaluation as thoroughly as Haskell does, but there are not many such languages that are in the mainstream, and so it's sort of a thing isolated to Haskell. The idea is we'll build a data structure, a circular data structure, which refers to itself. We'll build the hash map from name to node, but each of the nodes, because of laziness, won't actually get evaluated. And then we'll just sort of ask, hey, show me all the nodes in the tree. And the runtime system, Haskell's runtime system, will resolve the dependency order for us. By, if something's already been computed, you just get the answer. And if it hasn't been computed, then it'll resolve the thunk, which will involve looking up in the map any subtrees that it needs to look up, and if those already exist, you'll get them, and if they don't exist, then it'll look up those resolve those thunks, and it'll be lovely. So I think that that's the plan. So, what to do? How to do it? First up is we need to look back on day 5, please. Day 3? Day 3, please, because I will want a container again. Day 7, Cabal. There we go. So I want a hash map here, as we were saying. And because the input structure that we are parsing is a little bit more complicated than we have seen before, it might be, I think, in fact, would be best to use like Parsec or something. Haskell has phenomenal parsing libraries. They're outstanding. They make it really easy and almost fun to parse like string formats like this. But this input format is so simple that we can just use Haskell's pattern matching to parse it reasonably well, I think. And so that's what we will do, rather than introduce Parsec. I'll show you how pattern matching can let you write a parser quite easily. So here we go, source main. Yes. And the other thing is that I, oh, hang on, come on back to this program, this screen. I changed the skeleton that I had written for all Advent of Code programs. Remember, I built this little tiny Hello World thing for all days, and I replaced that with a skeleton that is just the tiniest bit more useful. It has the interact, show, and lines that we're using every time. It has skeleton definitions for part 1 and part 2 to enable it to do that. It gives us control.arrow, so I don't have to keep making those edits. But of course, most of the program still remains to be written. So first thing I would like to do, I guess, is import data.map.lazy. It's going to be very important that we use a lazy map because we're counting on these values being evaluated lazily. Import qualified as m. This is sort of like the thing you do with map, because the map libraries include names of functions that overlap with the ones in the Prelude, the standard library. And so if you just import the whole thing wholesale, you kind of get like some overlap, and it's people usually just import it as m, so you refer to things prefixed by m. And now the next thing to do is to define data types for what we're going to do. And the first one that I would like is one to represent the contents of a line of input. Without actually trying to build a whole tree, I just want a data structure that represents what did this line tell us. So we'll in fact call it line. Why not? Data line equals line of what? A string. String, that's the name. And an int, that's the weight. Let me just grab my puzzle input and double check that the weights are indeed all ints. Yes, very good, they are. So here we'll go put that into a file. 7. Fine, great. And we finally want a list of string, which is the subnodes. That's all the information that exists in one of these input lines. Now, the other data type that we will need, actually, let's make this derive a few. Actually, we shouldn't really need this to derive anything, but why not show? So, what's this about deriving, you say? I showed this off, or well, we did it a little bit in some of the previous examples, at least exercise 3, probably some others, when we defined a data type. There's this thing called type classes, which is sort of like interfaces in Java or C# or something like that, so for example, if we were to look at the REPL, we could say, tell me about show, please. And Haskell will tell you a lot. I forgot there's a million show instances. But basically, show is a class with these 3 functions. And a type A, in order to implement show, must have implementations of these 3 functions. In principle, like very simple definitions of show that you can write for yourself. Like you can support just this one, and the other 2 will be derived as defaults from that. But I think anyway. So it's basically show is the class of things that you can turn into strings if you want, and you can write show instances yourself. But for a number of the built-in type classes in Haskell, the compiler includes for you a method for automatically deriving a reasonable, simple implementation, and show is one of those. So we can say, I would like to be able to turn my line type into a string. And Haskell's like, fine. Okay. So actually, let's suppose I didn't do that. I could say, what is the type of line foo 5 empty string? It says, oh, well, that's a line. And I could say, let x equal this in case x of line A, B, C to A, whatever. And you can get stuff out of this by destructuring it, or pattern matching it. But we can't say show in, if I wanted to instead, I have that thing in show x. It says, well, I don't know how to show a line. You didn't tell me. So that's what this is all about, deriving show. I thought that it might be useful to be able to, and of course it print's a little bit silly, print. Actually, we can now at this time just say, here, what is this? Oh, I need an empty list. I can say, what is this? And now the REPL can print it for me, whereas before it couldn't, because we didn't tell it that it should be showable. And of course, we won't need to actually show lines to solve our problem, but I thought that I might run into some issues and want the thing to be showable to help debug them. So there you go. And I think we should need only one other interesting type, which is our tree. Data tree. Should we parameterize this type at all? No, probably not. We could be more generic, but there's no real need to. So a tree is what? It is a node containing a string and an int and a list of tree, I think. Now, in principle, this definition of a tree is not a very general purpose one because it's impossible to represent an empty tree. And so if I were writing this for a more general purpose sort of tree, I would say, oh, or it's an empty tree. That is another kind of valid tree, is an empty one. But here we won't have any empty trees, and so I think that, you know, who cares, right? We'll just exclude that possibility. So really, like, this is very, very much like this thing, right? It occurs to me, these two are so similar that maybe it's silly, but suppose I wanted to generalize this. I could say data, we can't call it a tree because we have a tree, but let's say we just called it a blob because I don't know what to call it yet. We could say a blob of t is equal to a blob, string, int, and a list of t. Right? Let's let this derive show as well. So all of this is correct and legal. And so if I wanted to, I think, I could just say that line is a type alias for a blob of string. Right? Like that's still correct? Oh, of course we can't derive anything here, but yeah. And a tree is also just a type alias. It is a blob of tree. That's probably not okay because of recursion in a type alias is probably not allowed. Yeah. But we could say new type tree equals like tree of blob of tree or something. Like we could do that if we wanted. So that's kind of interesting. I'm not sure that there's any real grand purpose to do this. It does let us sort of write down only in a single place that the interesting thing about a node is that it has a name and a weight. We don't have to repeat that in two different data types. I don't think that's a humongous win. So I'm going to go back to the by hand definition. But I think that it's kind of interesting. Well, let's go ahead and derive show on this as well. Why not, right? Yeah. So I think that that's an interesting thing to think of. Try to find generalizations everywhere that you can when programming, whether in Haskell or in something else, because when you recognize an interesting generalization, it means there's less code you have to write over again. The most general code is not always the best, but it's worth thinking about both. So these are the only types that we need. And now we will want a function called parse, which takes a string, takes a list of string, and produces as output a line, where the list of strings is going to be all of the words on the line, of course. So here we'll put map words, parse composed with words, probably. Yeah, each line we will want to call words on and parse the result of. And we will want also probably something called build tree that takes I'm fine to get to this later. Build tree is a function from list of line to a map from string to map of string and tree. Okay, what's wrong with my driving? Oh, I have it. This still says type, which is a data. Okay. So this now all is type correct, but still, of course, lacking quite a lot of implementation. And also, this part is not like... There we go. Fine. I don't know. Do you put the operators on the next line? It doesn't matter, of course, but what's more readable? I don't know. So, parse will pattern match on the input. Parse of name cons to weight cons to more is equal to a line of name and read of the weight where the result list is case more of if there's no things. Actually, yeah. If there are no things after the weight, if weight was the last word, then we just say nothing. And otherwise, if it is equal to the arrow symbol followed by children, then we will produce as output children, right? I think is it. Hang on. Does it have commas? It does. So we will just write map filter not equal comma over the children. Okay. So let's just let's just change this a bit right now, and we'll replace our main a little bit. I want to test our parsing function. I think it's probably correct. But instead of calling all these things, I just want to do nothing. So interact of show composed with map parse of words and lines. Still compiles. And if we now say run stack run dhc of source main fed from input.text, well, we receive, yeah, looks about right, yeah? Like, the final thing we get is a line for Swinafrut weighing 42 and having these 5 subprograms. And if we look at input.text, is that about right? Line Swinafrut, 5 subprograms weighing 44? Great. So, okay, we're reasonably confident that this parse function works. And by the way, isn't it just like so nice and simple? I love it. We don't need to use any weirdo regular expressions. We just call, like, split them into lines, split them into words, and then pattern match on the words. And it's all just gravy. It's great. I love it. So now we need build tree, which is the actual difficult part of this whole exercise. But I think, like I said, I think that by tying the knot, the whole thing just sort of resolves itself. So let's see. Build tree of lines equals what? It equals we have to be a little like sneaky here, I think. Equals m, I guess. Well, let's call it t for tree. Where? Now, this is a little bit silly. We say it equals t, where t equals something else. Why don't we just write something else here? Because we need a name for the value in order to let the value refer to itself, which is what I want to do. I want t to refer to itself, and so I need a name for t. This is sort of similar to the thing that you've seen me do in previous exercises of using go as a helper function. I say like, f of x equals go where? Go equals, right? Like, we're doing something very similar here with t, but instead of being a function, it's a value that we're defining. So where t equals map.fromList do, I guess? I don't know. Sure. I like I like monad comprehensions more than I like list comprehensions, even though they're the same. Maybe I'll go back and change it later if this turns out to be short and simple enough. We're going to say line, lines, only we're not going to do that, are we? We're going to say line, name, weight, children, drawn from lines. And this is a really weird place for Emacs to be indenting this line. I feel like here is much more natural, but Emacs puts it here. I don't know, who am I to argue, right? And we will produce as output, I think it's as simple as this. Return a key, which is the name. Wait, it will want a tuple, won't it? Of course it will. Name as the, so from list is a function in data.map which takes a list of tuples of key value pairs and produces a map from them. Well, we return the name and as the value a node with the same name and the same weight, but for children we will write map shit. How do I write this? All right. Haskell data.map. Here you guys go. So show me data.map, whatever, this one. Show me, I know we're looking at data.map strict. Data.map lazy has the same interface, so it doesn't really matter. How do I look up a thing? Null, size, member, not member. A lookup would give us back a maybe, which we don't want. Find with default. Oh, I think it's like right at the beginning, isn't it? It's like before all this other stuff? Yes. So this is what I was looking for. It takes a map and a key in that order. Huh? So this operator section here is a function. So this is an operator because its name has symbols instead of letters, and therefore it takes its first argument on the left and the rest of its arguments on the right. And when we write an operator section like this, we're saying this is a function. We're only finding one of the two arguments that it wants, and so that one, the t, is sort of baked in. And the second argument is sort of implicitly returned. So basically we have a function which, given a string, looks up that string in the map. And we are mapping that function over each of the children's names from the line. So, like, I think that's it, right? Seems very sketchy. Well, okay, does it compile? Yeah, it compiles. That's good news. So, let's just temporarily remove this and look at our tree. No, the tree is going to be way too big to really look at meaningfully. So let's not be so eager. Let's just, dang it. Here, look at all this stuff I wrote while you guys weren't looking. I don't know how I can make it more obvious to myself that I'm showing you the wrong screen. Like I can see there's a preview window like that I'm looking at of like what I'm recording, but I'm just like not looking at it when I'm doing this because it's not what I'm interested in. I'm focused on like the code that I'm writing. Anyway, so we wrote after we got back from looking at how map works. We wrote this, a function that takes a string and looks up the tree, looks up in the map the value at that string. And really this would be not so long a list comprehension, but this, I don't know, this is fine, I think. If we wrote it, we could instead write m dot from list of this for like this, basically, we could write. And I don't know where to put the line breaks in this, so I just like mostly don't write this, and I'm reasonably comfortable with how a monad comprehension looks instead. Forces me to write shorter lines and so on. Okay, so rather than like just trying to look at our tree and see if it was correct, let's just trust that it was correct and try to write part one. What does part one look like? Well, we're taking a tree. No, we're taking m.map string tree, which is sort of useful, I think. It would be sort of interesting, I think, to like store a little bit more information in the tree, wouldn't it? Like something you imagine we're going to need eventually is like, what's the weight of a subtree or something like that, right? Of a whole subtree rather than just a single node. And so I wonder if we could, like, let's parameterize our tree type so that it takes an extra a, some random thing. And that's going to be a slot that we can store any extra meta information we want at any node, at a node in the tree. Right now, we don't really have anything to store, and so we'll just store a unit. But I imagine that we might want to store, say, the weight of a subtree at this point. I was thinking I could somehow use it to store, like, what are the parents of this node, but, like, you can't really do that. We could, though, use it to store the number of nodes below this tree, right? So that's an interesting idea, actually. Let's do that. Instead of putting unit in there, let's just yeah. And then what we can do is just look through the map for the single node that has the largest number of subnodes, and that'll be the answer. We won't have to do anything like looking for a node that doesn't have any other nodes pointing at it. So how do we do that? When we build a node, we have to put something in it. So let's actually pull this up to here. Let child nodes equal this. And we'll let size equal 1 plus we'll write a quick little function here called meta. I don't know, it's to get the metadata of a tree node. Takes a tree of A and returns an A. I know, this is like not... This is not a very holistic approach, but whatever. Meta of node nothing nothing x nothing equals x. So we could do, there's a number of ways we could do this that would have been better. We could have like a record for this instead of a plain constructor. We could define a catamorphism for our tree type and then call meta with a catamorphism that like just extracts out this one value, but okay. Or we could even pattern match on it here, but I kind of want to write map meta over children. Sum of... That's not going to work. Sum of map meta over the children. And there's better ways to do that too, but okay, fine. So instead of a unit here, we'll put size, and here we'll put child nodes. Does this still compile, oh mighty Haskell Oracle? No. Expecting one more argument to type tree. Well, good point. We added a type argument to the tree type, but int. Oh, and also this should be to int, I suppose. Actually, what I should do is probably write a function called root or something that takes a tree like this and produces, yeah. So let's do that. Let's write a function called root that takes one of these and produces as output a tree of int. This is a little bit... I worry that we've used up... So I first put this little a here saying, oh, it'll hold whatever metadata we want, and we'll just sort of put like the weight that we're getting here, probably going to want later, we'll put that in. But now I'm using it for something like to find what the root is, and I was like, oh, that'll be fine, we'll just replace that. But if I want to do part 1 and part 2, we're going to actually need to store that. That's not just like some metadata about this tree, it's an important part of how we're building the tree to get its root. So suddenly seeming a little bit less impressive to do it this way. Yeah, I think that it might just make more sense to add another int parameter here. And have a tree size, takes a tree of A and returns an int. Kind of lame, I know. Tree size of something like this. Yeah, this really should just be a constructor or a record. These two functions suck. So we'll make it a node of node name is a string. What is this next one? It's the weight. I'm calling it node name and node weight. I'm not really convinced that this is a good idea, but my thinking is that it'll avoid name shadowing because we're using things like name and weight as local variables in places where I might want to be able to access these functions. Tree size is another int. Meta is an A. Node children is a listed tree. I guess this really should be node size, node meta. There we go. So I'm really not very comfortable with how to use records in Haskell. And so what I'm doing is probably some kind of anti-pattern, but I don't know what it is. Sorry. Okay, so we have all of this stuff. We can throw these functions away, thank goodness. Meta, and we'll just say tree size. Okay. Node name, weight, size. And unit, actually, because we still haven't put anything into our... We're now not using the meta slot anymore. We still have a meta slot, but we're not putting anything there yet. Okay, so fine. Leave part 1 alone for now, I guess. So what's how do we solve root now? Root of m equals minimum, no, maximum by, which I think is in data.list. Import data.list, maximum by, isn't there something like data.org that I want as well? Haskell data.list. Data.list, so maximum by is here, yes. Okay. Where's ord? Ordering is in data.ord. And it has like comparing or something like that. Comparing, yeah. So I think that what we want, showing maximum by again, yeah, it wants a function from A to ordering. And if we write comparing, yeah, okay. So we want that as well. Import data.ord. Maximum by comparing node size of, now how in a map do I get the values of the map? Data.map, here we go. I need to traverse. Map, don't want all that. Folds, yeah, okay. Conversion, elements. All elements of the map, okay. So that's what we want. Elements of them. And in fact, we can just divide that m entirely. Does this compile? M.elements. How about that? Tree size. That's right, it's called node size. How about this? Expecting too many arguments, expecting more arguments to tree. Yeah, that sounds right. We need it here. How do I... There's... I gotta ask Emacs some questions here. Next, no. Error, no. Problem, no. How do I get the next dang... Alright, help bindings, please. Next line, next error, Control X, and then this key. I tried Control C and that key. Okay. So what's going on this line? Why is Intero mode not highlighting here? We were in just regular old Haskell mode, that's why. Okay. Couldn't match char with tree. So we have a list of string. I see. I think. It should be child nodes here, not children. Got it. What else do you have? Okay, everything now compiles. Great. So I would just like part 1 to please be a string. And it will be node name dot root. Right? Give me a list of all the nodes in a tree. We'll find the one that's at the root and tell you its name. So, sounds good enough. Let's run it. A thing has occurred. Great. Let's double check when we read this in our input file. We should see WIAPJ occur exactly once. There it is on the left, and indeed it occurs nowhere else. So we're quite confident that this is the right answer. It was easy to check for being the right answer. Advent of code. Hooray! We got it. Okay, part 2. The programs explain the situation. They can't get down. Rather, they could get down if they weren't expending all of their energy trying to keep the tower balanced. Apparently, one program has the wrong weight, and until it's fixed, they're stuck here. For any program holding a disk, each program standing on that disk forms a subtower. Each of those subtowers are supposed to be the same weight, or the disk itself isn't balanced. The weight of a tower is the sum of the weights of the programs in the tower. Okay, so does that include the one that is holding up the tower or not? Okay. In the example above, UGML, Jigsaw, eBay, and Jupyter. So these all need to have the same weight, and they do. Fine. For TK, NK to be balanced. Yeah, so this is about what we sort of thought, I think. So, yeah. All these three things have to be the same. UGML and all the things above it, or under it, depending on how you look at things. Right. So, okay. That's interesting. So I think that what we will wish to do is to build a just slightly different tree using, in fact, the total weight of the subtree and putting that in our meta like we sort of expected we would do. Hang on, here we go. And then we'll traverse the tree from the top down, trying to find what exactly. So how do we determine which program is the one reporting the wrong weight? When we look at the weight of the root, its weight, of course, doesn't matter at all, because it doesn't have to balance with anything. Or wait, no. Does it? So each program, each of the subtowers have to be the same weight as each other, not as like the yeah, so in this computation they've given us here, they don't even care about TKNK, the root. Technique. Okay, so we can't, let's see. We'll start from the root, and we'll look at all of the leaves, right? All of its children. And one of them will be different than all of the others, and we'll follow that one. I see. So we'll have a function that takes a tree and returns. So what is it we're supposed to do? What would its weight need to be to balance the entire tower? So we will return. Yeah. So, well, wait a minute. At some point, we'll recurse down into that subtree, of course. That's all very simple. I'm just trying to think of what the basic condition is going to look like. And at any given iteration, we're going to have either all of the subtrees will be of the same weight, in which case we have found the problem and it's the root node, or else one of them will have a different weight than the others. Is that true? No. It's not true, I think. Because we might have a program with exactly one subnode where the subnode is reporting the wrong weight versus the node itself reporting the wrong weight. Is that possible? Can you tell the difference between those situations? I don't think you can tell the difference between those situations. Because if you have a node with just one child node, and you got to the node you're currently considering because it has the wrong weight, well, okay. I guess you got there because the node had a different weight than you expected. And that can't be caused by one of its children. I think I don't quite understand the problem yet. So each of the programs standing on its disk and all programs above it. The ones just above it? Yeah, the weight of a tower is the sum of the weights. So, alright, do we have any subtowers with just a single node? Do I need to worry about this at all? It looks like we actually don't. So it's sort of a confusing case, and it's one that I don't quite see explained in the problem definition, and it sounds like that's on purpose. Yeah, there just are not any nodes with only a single child, so we don't have to worry about that. Okay, so when we are recursing down this tree, we'll get to a node, and in fact, we no longer need to compose with root here. We can just take the root for granted. I thought I might still need the old tree, but I don't. Tree of A to string, and we'll just put a root down here. Okay, part 1 and part 2 will both just take the root node. We'll be done with the map. Okay. One program has the wrong weight. What does this mean exactly? I guess, okay, I kept for some reason imagining that this was about a program misreporting its weight somehow, but like that doesn't make any sense. There's just one of the programs weighs the wrong amount, and as a result, all of the towers supporting it weigh the wrong amount when you total them up. So we can just traverse down. Well, okay, there are going to be nodes with just 2 children though, right? And we can't say, oh, one of them weighs a different amount than the others. That one's the problem. How do we know what the right weight is? Maybe we don't need this total weight at all. Maybe I'm just totally crazy. Because... No, we do need a total weight. Okay. I was thinking that we could make a local correction once we find what's wrong, because it'll be breaking something locally. That's true, but it'll also be breaking something recursively downstream and or upstream, I guess. And that's how we'll even find the problem to begin with, I think. Yeah. So let's say we're looking at the root, and we determine that the weight of its... How many children does our root have, even? What the heck was it called? Wayakja. It has 5 children. So clearly, 4 of those children weigh the same thing, and a 5th weighs something different. So we can... From this, we can determine exactly what the 5th child should weigh. And we can recurse into it and say, hey, here's how much you should weigh. And it'll have a number of children. And it will say each of them should weigh 1/n of this total, right? The one that doesn't is the one that's broken. So that's how we resolve the question of having 2 subnodes. They're different, but which one is wrong? We know the answer from having started at the top node. Okay. This gives me some guidance into how we will direct this this search. So part 1 is a function from tree of A to int. And part 1 of T, let's see. Let's destructure it here. Well, no, we have part 1 of T is part 2, I should say, of T is probably part 2 of t equals the thing is, at some point we are going to want another recursive function that takes 2 parameters, right? The tree and what weight we expect it to have. I'm not sure. I'm doing something silly here somehow. Okay, well, let's just do it in like the most obvious way I can think of, and when it comes time to write the recursion, I guess I'll figure it out then. So part 2 of t is equal to, oh, of course, we can't do this until we've added the subtree weighting information to the tree. So we'll just use the node meta slot for that. I don't know. Again, this is like a totally bonkers way to have done things. But okay, whatever. And let's see, we get out all this stuff, child nodes, now we have this, we have total weight equals weight plus map node weight over the child nodes, and we'll just here put total weight. This is actually producing a tree now. I forgot to commit part 1. Didn't I? Did. Okay, let's just get rid of this for now. Okay, this is about everything. Git add, git commit -m day 7 part 1. And now we'll undo that deletion and put some stuff back here. Tree of int. Why are you upset here? Couldn't match. Oh, some of this, thank you. Okay, and so here we will say I need actually a tree of int, though. So part 2 of t is I guess, what exactly, how do we compute the desired size of these things? Majority vote, right? I guess, how exactly is the right way to implement that? Let's see. We can write a map from weight to number of times that it occurred? There's got to be some simpler way to do this. I figured out. We can sort the weights and take the third weight. That'll definitely, because the wrong weight will either be too large or too small, so it'll be on the left or the right. So actually the second weight, I guess, is best. Since we need our root node to have at least 3 node subnodes for this problem to make sense. Therefore, we'll look at the middle one. So we'll say part 2 of tree of name weight is, which we also don't care about. Size we don't care about. Meta we don't care about. Yeah, that's true. And nodes, I guess, is let weights equal map node weight over nodes. And we'll sort this as well, I guess. I guess that's in data.list, huh? Sort composed with okay. What else do I need? Goal weight equal weights at index 1. It's like that. I forgot. You index things in Haskell lists so rarely, I sort of forgot how to do it. And now okay, here's what we can do. We can say weight sub 1. So that's the goal weight we expect each of the children node to have. Plus W. What am I doing? I'm trying to switch from this part 2, which is our top level function that has to start from not knowing what the expected weight is, into a new recursive function that is told, here's the weight you should have, and here's your node, why don't you have that weight? So I'm thinking that I'll compute the weight that the total weight that the root node would have if all of its child nodes weighed the same. So this is actually going to be W plus length nodes times this. Okay, does that make sense? So we say, look up, oh wait. Yeah, right, the second node is guaranteed to have the correct weight. So if we take that correct weight and multiply it by the number of nodes and add in the weight of the root node, we will know how much the root node should weigh. And we'll use that as a goal to seed our recursive function. And that function will look at all of the children and see which one is the wrong weight and recurse from there. Let's call it interrogate, shall we? In interrogate root goal weight. Okay. Oh, this should be node, of course. Thank you, Intero, for letting me know. And it says, yes, of course, you haven't defined interrogate. I know. Interrogate is a function taking a tree of int and producing an int. No, it takes in another int and produces an int. Interrogate of interrogate of t and a goal is, let's see. We don't have any nodes with one child, so we don't have to worry about that. So first, what do we want to do? If the two children have the same weight, or if all of the children have the same weight, then we're done. I'm trying to figure out if I can first detect whether the root node itself has the wrong weight. Before descending into the children, because if I can tell that the root node has the right weight, then I can compute quite easily what the expected weight for each child should be, and just descend into the one node that doesn't have that weight. So hang on. Are there... I forget already. Yes, there are nodes with exactly 2 children. Maybe I'm making this harder than it has to be. What will be the properties of a node with an incorrect weight when we're looking around in that area? What will we see? We'll see that any children nodes it has, if any, all have the same weight. Right? Or it will have no children at all, which is the same thing as saying all of its children nodes have the same weight. And in that case, the weight that it should have is simply the difference between the goal weight and its current weight. Or is just the goal weight, actually, right? Yeah. Well, no. It'll be the goal weight minus the weights of its children. Okay. So that's interesting. Gosh, I'm going to be rewriting a bunch of what was part 2 here, and it makes me feel sad. But it seems like a relatively harmless thing to do. I guess I'm not going to rewrite that much, because I can't count on one of them being correct. So let's destructure this into node. Don't care about the name. We do care about its weight. I think. Do we? No, we don't even care about its weight. That's interesting. We care about its total weight very much. What's the third argument here? Size. We don't care about that. But we do care about its current total weight and its children. Right? And actually, we can do this. We can say if it is the case that the weight of all the children is the same. How do you... I have a list. I guess I have this, right? I want to know if they're all the same. And that just doesn't exist, huh? Fine, I guess. What the heck is on this key anyway? Do I want it? No. How do I unbind this? Let's do that real quick. Global unset key keyboard meta at. And likewise for meta exclamation point keys. These are the keys that I'm using to manipulate which window you guys are looking at, and I don't want Emacs paying attention to them. Great, okay, it worked. I should put that in my config file, but whatever. This session is going to stay open for forever, so we can just... Anyway, whatever, doesn't matter. So we can say here, if the children all have the same weight, and how would we do that? I guess we would say if length of nub of map node meta of children equals 1, then we have the answer. All the children weigh the same. Ooh, let's actually say less than or equal to 1, because it could be 0 if there are no children. And actually we do care about the node's weight. So total weight and weight here. No, we don't, right. Because we don't need to compute the delta, we just need to say... Yes, we do. We care about a delta. Well, we'll take this and make it into a where file, where child weights. Where child weights equals this. Equals goal minus sum of child weights. Fine. Otherwise, equals, I don't know, undivided. So I think that that's our base case, is we've gotten to... We've gotten to a point in the tree where all the children have the same weight. And that means none of them can be the problem. The current node must be the problem. And the weight that it should have is the goal weight minus the sum of all the children. So, given that that didn't happen, the children don't all have the same weight, we can say what? Otherwise equals, let child goal, I guess, equal goal minus the weight of the current node divided by the way, the reason we're not using this here to divide, and in previous puzzles we also used div, this is the divide operator for fractional things, floating points or fractions or what have you. This is the integer division operator for working with integral things. So goal minus w divided by the length of children. And you know what? We can just put that in the where clause as well. Why not, right? Let is so complicated. Let's just put it all down there. And we'll just say it is equal to interrogate the first node in children that does not have the same total weight as the child goal. Right? That seems about right. We're calling head here, which is like not great, but you know, whatever. Head of child where child comes from children, and it is the case that child goal is not equal to node meta of child. And pass that the goal that we want. Right? Does this actually compile? Astounding. It does. Could have fooled me. I'm not at all confident that this will be correct, but I'd like to see what happens. Oh, that was fast. 64,000? That's very large. I don't think it's right at all. Oh, well, actually, there's Jizawid. It's got a very high size. Maybe it should be much heavier for some reason. That seems very, very large, though. I'm a little bit dubious. Well, there's, okay, 61,000. So you know what? Let's do something a little bit different here. We'll change interrogate a tiny bit, and therefore also part 2, to return a string int. I would like to just know which node is it that should have its weight set to this outrageously large value. Node n n. Okay. And let's try this one more time. It's Iphigenia is the offending node. Hang on, wrong. Give me back my input, please. Iphigenia. 32. Really? Okay, sure. It's off by quite a lot, I guess you could say. But, like, I don't see any reason to doubt this result. Okay, well, I guess we'll try it. If it's wrong, then Advent of Code will tell us, right? What would its weight need to be to balance the whole tower? It's too high. Okay. Alright. Well, I mean, I can't say that I'm surprised. I've got a pretty silly smile on my face at the absurdity of that answer. But it's not, like, totally absurd, right? I don't know. Just, How could we visualize what's going on, perhaps? Like, it seems like that would help. Here we go, main. Oops, didn't mean to highlight the whole file. We could print some stuff when we get here, I guess, at each step of interrogating. I don't love it. But I'm not sure what else to do. Like, I can obviously just, like, read this and look for bugs, but you don't always find those. So when we're calling node meta. Goal, so the weight that it should have is the goal minus the sum of all its child weights to make everything balance. Yeah, that sounds right. It seems like this might be it might help to draw this in GraphViz or something, which I'm not like a super expert at doing, sadly. But getting to look at what the tree looks like, I bet would tell us something pretty interesting. So are we computing the child goal incorrectly, perhaps? So child weights is just map node meta over children. I'm pretty happy with that. It's the total weight. Maybe actually part 2 is wrong. I did this one in a bit of a hurry, right? So the weight that we expect the root to have is its own weight plus yeah, okay, we're doing things in the right order. Its own weight plus the number of children times the weight of the well-behaved children, right? Maybe I'm just wrong when I say that to find the misbehaving node, we should descend until we find one where all the children are the same weight. But I think that's right. At any given level, if all of the children are already the same weight, same total weight, and it is the case that higher up in the tree there is an imbalance, then the node that we are looking at must be the cause of the imbalance. But maybe I did start with a faulty assumption, which was that there is necessarily an imbalance at the very root of the tower. Is it possible that the root is currently balanced even though one of its subtrees is imbalanced? I don't think that's possible, because then there's no way we could adjust the weight of any node at all without disrupting the root. So it must be the case that the root is currently imbalanced. Given so much, one of its children must have a different weight than all the others. Like, I feel like my recursive strategy is correct, and I just like have somehow set the wrong goal weight, maybe? Yeah, I think that I'm just gonna like try putting doing a little bit of debugging in here, and like, I'm not good at debugging Haskell. I prefer to just write programs that work the first time, and then you don't have to. There's a library called debug.trace that lets you kind of cheat Haskell's referential transparency parency and purity guarantees by inserting print statements attached to your expressions that like get evaluated even though it's like not allowed in the type system. It's not very reliable. You shouldn't use it for like production logging or anything, but it works fine for tracking things down, and then later removing the trace. It's not something you would leave in like logging. So we'll just write trace found offender. There you go. So trace takes a string and a value, and it prints the string, then returns the value. You can't make it a separate statement because there's no such thing as statements in Haskell. Rather, it's a function that takes the thing you want to print and the thing you want to return, and itself prints the thing and returns the value. So now we have to like put a trace here, which is a little bit more exciting. We say trace node. Oh my god, get out of here, Intero. I'll fix all the types later. Node n imbalanced children way plus map show of child weights. Not map show exactly. Actually, I think I can just like, yeah, I kind of do want that. This and this. Okay. Yeah, and then we need like one of those crazy functions from data.list. Fine, Hoogle. I have a list of string and I want a string. Unlines, unwords. Perfect. That's exactly what I wanted. Unwords. There we go. So unwords is sort of the opposite of the words function, where words takes a string and gives you back a list of the words in it. Unwords takes a list of things and gives you back a string where they're separated by spaces. Okay, so it's not a very like amazing debug. Oops, I don't want a shell in Emacs. Get out of here. I wanted to switch to my existing shell. And we do this, and we get like this. This is interesting. Node Weiapta unbalanced. Children weigh this amount. Totally different amounts. So clearly, the tree that I built is completely bonkers. That's the problem. The problem is not how we are descending the tree, but how we built the tree in the first place. It's just completely wrong. Great. I am thrilled to know this. Why did that happen? Build tree. We built a tree int. Yes? We computed the total weight. We got the weight from the line. We looked up all the child nodes. We added the weight to... this should have been node meta, because we want their total weight, not the weight of the single node. Okay, this is much more promising now. If we run this again, we say Weiapta is imbalanced. Its children weigh different amounts. And we, I guess, descended into the very first one and found that all of its children weighed the same amount. This still looks quite wrong, though. Doesn't it? What's going on with Jizdwood in, Okay, let's put a children way thing in there before I try this as an answer, so that I'm a little bit more convinced in the answer. Let's write a little function here for this. Why is typing not working, please? Hello? Oh, I see. I must hit Control-Z at some point. What's going on? Is Intero busy? Help. Why, like, typing is really slow and bad. Is it my connection? No, this is fine. Emacs has just, like, gone in a hole and died. Why? It can hear me saying quit. And occasionally a keystroke gets through. I don't understand this at all. Alright, well, Emacs isn't working right now. I'm going to just try this answer. That's not right either. Okay, so we have some more debugging to do. But at the moment, Emacs isn't working. So, and this episode has gotten rather long. So I'm going to just call this episode now. We'll get back to debugging in the next episode. Thanks for watching, and I'll see you next time.